Well, we've quickly arrived at one of my favorite topics in the course, the skeleton. The skeleton is a fascinating collection of living organs. Did you know bones are individual organs? And the combination of bones along with the ligaments and cartilages that hold them together make up the skeletal system. Because the skeleton forms the basic structural framework of the body, just seeing the outward shape and the pattern of movement of any animal with bones tells you a lot about that organism. And because bones and teeth are the most durable parts of the body, we also know a lot about the evolution of humans and other bony animals from the history left in their fossilized skeletons. Features like how they stood, how they moved, how big their eyes were, and where those eyes were placed, and how large their brain was relative to body size. Not only does the skeleton support the varied soft tissues that make up the rest of the body, but because of the joints between them, bones serve as levers in the leverage systems that cause movement. Muscles supply the force, and the joints serve as the fulcrums in these leverage systems. Now, we'll talk a lot more about those specific roles in future lessons since we're studying musculoskeletal anatomy. But can you think of any other functions of the skeleton? Consider the rib cage or the skull, and you'll recognize the protective role that the bones provide for more vulnerable and soft internal organs. You might also know that one type of our bone marrow, known as red marrow, found in flat bones and in the ends of long bones, is a source for the production of new blood cells that move out of the bones and enter circulation. The major long bones of the body also house yellow marrow, which is the fatty marrow within the hollow shafts of bones like the femur or the humerus. This yellow marrow serves as an energy reserve since fats have over twice the caloric value of proteins or carbohydrates. But among the most important roles of the skeleton, and the one that many scientists believe was the original function of bone within the animal body, is to serve as an internal warehouse of minerals. You probably know that calcium is the primary mineral in bone, but bone also houses phosphate salts, with phosphorus being another mineral important to good health. Other essential salts and minerals in bone include carbonates, sodium, magnesium, and potassium. Still, other minerals are held in the skeleton in trace amounts. These include iron, copper, zinc, manganese, fluoride, strontium, and boron, all of which are important in various metabolic and enzymatic pathways. You might be wondering why experts in animal evolution hold that the original function of bone was for mineral storage. Let's just consider calcium as one example. Calcium and phosphate salts crystallize and together with other minerals make bones hard and durable. But calcium is also a required ingredient in the reactions that cause all of our muscle activity, including our heartbeat. Calcium is also necessary for the propagation of electrical signals in the nervous system. And it also aids in the body's chemical messaging with the release of hormones from glands. As if that weren't enough, calcium is also necessary for normal blood clotting so that minor injuries don't result in the loss of too much blood. So what better way for animals to have a supply of this important mineral than storing it within the body with constant and ready access, even between meals? The point is that these minerals don't just sit there. Remember, bone is living tissue. When we have plenty of calcium in the blood, say after we eat a spinach salad and drink a glass of milk, we're able to store some of that incoming calcium in our bones, at least when we're young. Cells of the bone called osteoblasts, under the influence of hormones, remove some of that calcium from the blood and sock it away in the bone for a later time. Then, if we go the rest of the day without dairy products, without sardines or canned salmon with its small edible bones, or if we eat no dark leafy greens, then blood levels of calcium fall. In this case, we have hormones that tell other bone cells, called osteoclasts, to get some of the calcium out of bone storage and put it back into the blood. Now, these cells don't rob the bone to the point where your skeleton goes rubbery. Instead, they take just what they need to keep the blood calcium levels at their optimal range for all of the other body processes that need it. This cycling of minerals is called bone remodeling, and it's an important part of bone maintenance. About 10% of our bone mineral is turned over each year, so your skeleton is constantly renewed by the process of remodeling. In fact, the minerals currently in your bone represent only about the last 10 years of your life, which can be useful in my forensic work, but that's a story for another day. Now, if the mention of dark greens like spinach surprises you as a source of calcium, consider this. After being weaned, a cow never drinks milk again, doesn't eat yogurt or tuna, yet still builds a massive, sturdy skeleton. Calcium is not only contained in some greens, but also in certain seeds, like poppy, sesame, and chia. It's in beans and lentils, almonds and hazelnuts, edamame and tofu, and even some fruits like figs, apricots, and kiwi. Now consider this. I mentioned that we are best able to move incoming calcium from sources like these into the bone when we're young. That's during our childhood, teenage years, and early adulthood. We typically reach peak bone mass as we approach age 30, and then start to lose bone density by age 40. Remember that I said that we need a steady supply and consistent level of calcium in our blood for various functions like muscle contraction and nerve impulse conduction? Well, if we don't take in enough dietary calcium to offset our body's daily needs, then more calcium is taken from our bones than we replace through our diet. And when this happens, bones steadily lose their mineral content. And while we can limit or slow bone loss to some degree by weight-bearing exercise and a good diet, a certain amount of bone loss is inevitable, especially since the ability to build new bone starts a steady decline past around age 40. Sadly, we continue to take calcium out to support physiological needs, but we lose the ability to replace it in bone like we could when we were younger. The time to build a strong skeleton then, strong enough to last a lifetime, is when we're young. So what can be done when you're young to keep blood calcium at levels that won't lead to a loss of bone minerals when you're older? The best thing to do is eat a good diet and supplement with calcium tablets or calcium-fortified foods and drinks. That, plus exercise, will keep your blood levels high enough to prevent the body's physiologic needs from taking it out of your bones. Remember, since we naturally lose the ability to build bone as we age, we can only hope to maintain our bone calcium levels through a calcium-rich diet and weight-bearing exercise. In addition to talking about what's good for bones, there are factors and habits that can negatively impact bone strength and even accelerate bone loss. These include smoking, excessive alcohol consumption, poor diet, and a sedentary lifestyle. And not to be a downer here, but even without any of those negative factors, at some point, bone mineral loss is inevitable. Women in particular have accelerated bone loss after they hit menopause, which on a worldwide average happens at about age 50, occurring at slightly older ages in developed countries and a bit earlier in less developed parts of the world. This postmenopausal bone loss is because the female hormone estrogen has protective effects that keep bone strong, but estrogen is no longer produced after menopause. At that point, women begin to lose bone minerals at an increased rate compared to before menopause, or when compared to men of the same age. Given that women can spend about a third of their lives in a postmenopausal state, osteoporosis is a global health concern for females. And men also have bone loss, and by about age 65 or 70, their rates of skeletal demineralization are about the same as in women, leading to osteoporosis. Since women started their bone loss sooner, however, they're at greater risk of more advanced osteoporosis. And when bone is demineralized by osteoporosis, someone's own body weight can be enough to cause a fracture. This is called a pathological fracture because the bone was already weakened by another condition, as opposed to a fracture that's caused by trauma. When bones are that weak, they often have difficulty healing, especially if the blood supply to the bone is disrupted by the fracture. Now, let's talk a bit more about the construction of bone. Bone has widely scattered living cells that are surrounded by and embedded within a connective tissue matrix. For the most part, the cells produce this matrix bed and then they lie in it. The matrix is mostly composed of a variety of calcium phosphate salts, collectively called hydroxyapatite. These minerals are crystallized around strands of the protein collagen. Now, depending on age and health, the overall chemical breakdown of bone is generally about 50% inorganic minerals, around 25% organic compounds, mostly the collagen, and about 25% water, much of which is inside the bone cells. A good analogy is that the makeup of bone is similar to fiberglass. Bone's collagen fibers, like the fibers in fiberglass, give bone some flexibility and resiliency. Now, you may not think of bone as being flexible, but it definitely bends before it breaks. It really takes a lot of force to break healthy bone. The mineral part of the matrix, on the other hand, gives bone its strength, just like the glass in fiberglass, but it's brittle. It's the combination of the flexible collagen and strong minerals that give bone its remarkable properties. Now, here's something interesting you can try at home to analyze bone's makeup and resulting properties. Get a pair of chicken leg or thigh bones, or maybe a pair of rib bones. Both bones should be from the same animal and be about the same size. Remove as much meat as possible, and then put one of the bones in a container of vinegar, enough to cover the bone for several days to maybe a week or so. But use a container with a lid or cover it with plastic because it will get smelly. Now, if you want and you don't mind the smell, you could take it out of the vinegar each day to see the changes over time. After a while, when you take it out, the bone will have the same shape, but it will be flexible. You might even be able to tie a knot in it. This is because the acids in the vinegar demineralize the bone. In other words, the vinegar leaches out the calcium in the bone matrix, leaving all the flexibility of bone, but without the strength. Now, in the meantime, take the other bone of the pair and put it in a 400-degree oven for an hour or so. And when it cools off, you'll find that the bone is really brittle and might even scratch easily with your fingernail or a fork. It often gets so brittle that if you put it in a paper towel and step on it, the bone will likely break. This is because the heat denatured the collagen proteins and cooked off all the water, leaving only the brittle matrix behind. Remember, the minerals give bone its strength while the collagen provides some flexibility. And it's the combination of the two that gives support with resiliency. But this is all on the microscopic and chemical level. So, as important as that is to understand the skeleton, let's make our way back to gross anatomy. Do you have any idea how many bones there are in the human body? If you had anatomy and physiology in the past, the number 206 might come to mind. But do you know that's actually an average among humans and only adult humans? The number actually varies with age. There's a general pattern of growth and development in which the skeleton starts as other types of connective tissue, including cartilage. Then, throughout our prenatal and postnatal development, some of that cartilage begins to ossify, which means it transitions to bone. And in a typical long bone, like the humerus of the upper arm or femur of the thigh, It doesn't just ossify in a single bony element. First, the shaft, called the diaphysis in anatomy, starts turning to bone, becoming what's known as the bone's primary center of ossification. Then the two ends, called epiphyses, turn to bone, becoming secondary centers of ossification. This process leaves bridges of cartilage between the shaft and its two ends, and these are the bone's growth plates. You've probably heard of those. They're the regions where the bone continues to grow in length during childhood. Eventually, when the bone has achieved its genetically programmed length, provided good health and nutrition, the growth plates close up, fusing the diaphysis to the epiphyses and resulting in a single bone. Now, long bones of the body grow that way. The skull and other types of bone form from other soft tissues in different patterns of ossification. But back to the bone count. When these long bones are developing and still composed of multiple different bony elements, technically we actually have far more than 206 bones. In the third trimester of fetal life, if all ossification centers are counted, at the highest point, the number is about 800 tiny bones. Bones in quotes there, since they would be better described as 800 separate centers of ossification or bits of bone in formation. Some of these bony elements fuse together in utero, resulting in about 450 bones at birth. But sources vary on the exact numbers. In fact, over anatomical history, sources have varied significantly, even in the total bone count in the adult skeleton. The total attributed from Galen's work was 248, whereas Vesalius counted 307, and the modern number is 206. Now, it wasn't that the number changed throughout the past few thousand years, but depended on how they counted, like counting the sternum as one bone or two. But even after the adult skeleton is formed and the last growth region at the medial ends of the clavicle closes, the number of bones can still change. For instance, arthritis can fuse vertebrae in the spine. The 22 bones of the skull often fuse together in old age. And arthritis or injury can fuse small elements like finger and toe bones. So technically, once that happens, an individual doesn't really have 206 separate bones anymore. Still, aside from the changes that occur with age, 206 is an average number of bones in the normal adult. Individuals can be born with extra bones or fewer bones. I see that in my forensic work, and it's not even all that rare. In fact, I look for it because unusual skeletal features can help get a person identified. For example, we may suspect who the person is from other clues, like an ID card or simply the location where they're found. And if we can find an X-ray of that suspected person that includes the unusual features seen in the morgue, we can match those up and get a head start on identification long before the DNA results are back. In fact, for any given anatomical feature, there's what I call the 70% rule. It's estimated that only 70% of us have the by-the-book pattern for a given structure, meaning that 30% of people have anomalies. So if 100 people are watching this course now, that means that about 70 of them have 206 bones, and 30 of them probably have some variation in bone number. And not just from age or maybe injury that fused bones, but congenitally from their own genetics and development. And when you consider how many different anatomical structures we each have, and that approximately 30% of us have anomalies for each one of those, it's no wonder we see so much diversity in ourselves and in each other. I find that equally exciting and amazing, both to think about and to see. And despite 30 years of teaching gross anatomy, I still see things I've never seen before. Students will call me over to their lab table and ask, "What is this muscle?" And I say, "I have no idea, but it's really cool, isn't it?" And they'll ask, "Well, what should we call it?" I say, "Name it after yourself, just like the early anatomists did." but we can usually look up the anomaly and find it in reference lists of so-called normal variants, which is kind of an oxymoron, I guess. Some of these unusual features are common enough that science has statistics for how often they occur. I have a colleague that has coined one of my favorite gross anatomy sayings: the only constant in anatomy is variation. Now, this is a course to learn about musculoskeletal anatomy. So you might feel defeated thinking, we have to learn about 206 bones? Well, there are some conveniences to it. For one thing, there are a lot of repeating themes in the body, like 24 individual vertebrae within the spine, which have many similar features, and 12 pairs of ribs that likewise have much in common with each other. And there are 56 bones called phalanges that make up our fingers and toes and have great similarities. And those 56 alone are over a fourth of the typical 206 bones right there. We also have bilateral symmetry in our favor. So because the right and left sides of the body are basically mirror images, once you learn one side, you've learned the other side too. And finally, due to our four-limbed tetrapod ancestry, the upper limb and lower limb have much in common, as we'll see. Even with all these shortcuts, we're not going to learn all 206 bones at once. Instead, we're going to study anatomy regionally, learning the individual bones of a given section of the body when we study it. In terms of general principles, one of the things that's often taught in a standard anatomy and physiology course is the classification of bones by shape. There are 4 shape categories, and they are long bones like the femur and humerus of the limbs, flat bones like some in the skull, short bones, which are smaller boxy bones like the carpals in the wrist, and irregular bones like the vertebrae that don't really fit in any of the other categories very well. But I really don't take that approach in my courses because I don't see much utility in it. The only reason I see to understand long bones versus short or flat bones has to do with the ways in which they develop and ossify. And while we briefly address the development of long bones, we don't typically cover the ossification process in a gross anatomy course. One general concept we will use in this course is the contrast between the axial part of the skeleton and the appendicular skeleton. The axial bones are those that make up the main longitudinal axis of the skeleton. These include the 22 bones of the skull, the 6 tiny ossicles in the ears, the single hyoid bone in the neck, the 26 bones of the vertebral column, and that's the 24 individual vertebrae plus the sacrum and coccyx, or tailbone as it's called, the 24 ribs, and the sternum. Now that's a total of 80 bones. The appendicular skeleton, on the other hand, includes the 30 bones in each upper limb, the 30 bones in each lower limb, as well as the 2 clavicles and 2 scapulae of the pectoral girdle, and the pair of pelvic bones that attach our lower limbs to the axial skeleton. So the appendicular total is 126 bones. If we've done the math right, that's 206, when the appendicular and the axial totals are combined. Now, another general concept we should cover has to do with bony landmarks. There are some standard terms for bone features, such as foramen, tubercle, condyle, and then adjectives are used to specify those on a given bone. I guess an overarching scheme of bony landmarks would boil down to 3 main categories: projections, depressions, and openings. Depressions and projections are typical of muscle attachment sites and joint surfaces, while openings will transmit arteries, nerves, and veins. Learning the general bony landmark terms in advance will help prevent confusion, since numerous bones have tubercles, notches, heads, facets, and so forth. So without understanding these are rather generic terms, students often say, but wait, I thought the tubercle was on the humerus. How is it now on the ribs? Or they'll say, there are condyles on the femur, so why are they also on the tibia? Keep in mind that some of the specific landmarks also use anatomical directional terms, like lateral, medial, superior, and inferior that we learned in the last lesson. Here are some examples. Let's look at openings first. Here's the infraorbital foramen. It's a hole inferior to the eye socket, which is anatomically known as the orbit. Conveniently, the infraorbital nerve, artery, and vein all pass through it. And by our rule of adjectives, if we have an infraorbital foramen, we also have a supraorbital foramen. Now, sometimes that's an incomplete opening. So many of us have a supraorbital notch rather than a supraorbital foramen. This is the obturator foramen, the largest foramen in the body. But despite its large size, very little passes through it. And this is the external auditory meatus. That's a tube-like passage lined with skin through which sound waves pass to reach the eardrum. Now, inside the skull, there's an internal auditory meatus, which satisfies the rule of adjectives. In terms of depressions, here's the intertubercular groove or sulcus of the humerus. You'll hear both of those used. It's called that because it's between the greater tubercle of the humerus and the lesser tubercle of the humerus. So since inter means between, and it's a groove between those tubercles, the intertubercular groove is a good name for it. Another depression is the glenoid fossa. That's the name for the shallow socket of the shoulder joint, which the humerus fits into. And this shallow depression is the iliac fossa, named for the part of the pelvis it's on, the ilium. The muscle that originates here is called iliacus. As the skeleton is the framework of the body, the names of the bones are the basis for the names of many other structures. That's why bones are typically covered first in musculoskeletal anatomy study, or really when you study any form of anatomy. As for projections, we already mentioned the greater tubercle and the lesser tubercle of the humerus, and there's that rule of adjectives. The scapula has a glenoid fossa, and it also has a supraglenoid tubercle above that socket, or better yet, superior to that socket. So what else do you suppose it has inferior to that socket? If you said infraglenoid tubercle, you're right. These large projections on either side of the elbow are the medial and lateral epicondyles sticking out on either side of the humerus above the elbow joint region. So you see medial and lateral being used. These examples should give you an idea that learning the types of bony landmarks, condyles, foramen, and facets, will make a good foundation for learning the names of specific bone features later in the course. So where do these bony landmarks come from? When I ask that question, my students usually answer that the landmarks are there so muscles can attach to them. But that's not exactly the case. To some extent, these projections, trochanters, tubercles, processes, they are there because muscles attach to them. Now that might sound like double talk or a fine point, but really it's not. The landmarks don't develop to facilitate the muscle attachment. They grow because bone's reaction to stress is to build more bone matrix. Remember, the matrix is composed of the collagen fibers surrounded by calcium phosphate salts. That addition of more bone matrix in response to stress strengthens the bone. Essentially, this relates to a concept in anatomy known as Wolff's Law, which states that bone will adapt to the loads under which it's placed. This is why stress, like weight-bearing exercise, is healthy for bones, within reason, of course. It's also why inactivity causes bone atrophy, whether it's astronauts on the space station, a bedridden patient, or a person in a cast for 6 weeks. Human genetics lays down bone in predictable patterns in the skeleton. Genetics also causes muscles to attach in the same places in all of us, within that 70% rule of what's typical. But from the outset, the fetal skeleton has long bones that are very simple in shape. They look like tiny sticks and lack the typical landmarks of adult bones. As babies begin to use their muscles, the muscles pull on the bone underlying their attachments, and by Wolff's Law, the stimulation actually helps build the bony landmarks typical of the adult skeleton. Most people think of the skeleton as static, but it is changing and responsive throughout life, in subtle ways, such as its mineral content, and in obvious ways as well. And I find that fascinating.